This is video on kinematics of particle. This is seventh video in the series, and here we are going to solve some problems using work energy principle, the kinematics of particle problems. Now you see there is a video part 6 which talks about the formula which we are going to use in this video. So you may want to just have a look at part 6, which is a real short video, about 3 to 4 minutes. And then see here, this is problems video 1, means some more videos are there on problems where there will be more problems. Alright, have a look. First problem, it says a block weighing 2500 Newton rests on level horizontal plane. That is, this is a plane, this is a block, it weighs 2500 Newton and it is resting here, and this plane has coefficient of friction 0.2. Now the block is pulled by a force of 1000 newtons. See, this is a 1000 newtons force is pulling the block towards right, acting at an angle of 30 degrees to horizontal. Well, the force is acting at angle of 30 degrees, not in horizontal direction, but acting at an angle. No problem. Then what is asked is find the velocity of the block after it has moved 30 meters starting from rest. So at 1, in position 1, the block is at rest. Because you are pulling it, block will move towards right and go to position 2, and this distance is 30 meters. What you are asked is when it reaches position 2, what will be its velocity? This is the part 1 question. Second question is, if the force of 1000 Newton is then removed, if force of 1000 Newton is then removed, how much further will it move? How much further will it move? So this second part we'll do in the next slide. Let's concentrate on finding what is the velocity at this point, at this position 2. Okay, so we use equation which we derived in the previous video, and just to refresh your memories, left hand side black terms represent sum total of energy for position 1. Black terms on the right side represent sum total of energy for position 2. We are using principle of work energy principle, which says the energy sum total should be same. Only on the left side we are adding F into D, that is energy given to this system by external force, and here we are adding energy eaten up by the frictional force, and this completes our energy balance equation which we are going to apply to this problem. So now F into D we write as 1000 cos 30 into 30, meaning what this 1000 cos 30 is a force in the direction of 30 meter, and that force into distance is the work done, and that is the energy given to the system. So that is Fd, and that is 1000 cos 30 into 30. Now all these terms mgh half mv square half kx square, which represents sum total of energy for the body in position 1, are 0, 0 and 0. Reason, for mgh, that is potential energy, we are going to take this level as reference and the body is at the reference. So 0. Body starts from rest, so half mv square is 0, and there is no spring in the body, so half kx square is 0. Okay, have a look at right side. mgh is still 0 because body even after coming to position 2 is at the same level, so same reference level, so mgh is 0. Half mv square exists because by this time body has achieved some velocity, and half kx square is 0 because there is no spring anywhere, and then is frictional force into d, distance is 30, and frictional force is always 0.2 mu times the normal reaction. Normal reaction here we can calculate by simple statics, writing sigma fy equal to 0 in vertical direction. What we'll get is 2500 is equal to r plus 1000 sine 30. That gives me rs 2000. And this r I plug in here, and I get my V, which is 10.47 meters per second. As you all know, the M will be 2500 by G. M will be 2500 by G, the mass. Okay, because 2500 Newton is the weight. All right, so we got our velocity. We got our velocity at position 2. At position 2. Now let's look at the second part. If at this stage the force 1000 Newton is removed, how much further will it move? You all will agree that because it has velocity towards its right, it will move on. So let me redraw the figure here, wherein position 2 in the previous slide has become position 1 in this side. The force is removed. And position 2 is at a distance d where the body has stopped. Now between these two, again I write my energy equation, which says F into d, but F into d is 0 this time because no external force. Mg is 0 because same level. Half mv square exists because we have worked out just now in the previous slide that we are going to use, and half kx square is 0 because no spring. On the right hand side, these mgh, half mv square, half kx square, all of them are 0. Reason, mgh 0 because same level, half mv square 0 because body stopped, and half kx square 0 because there is no spring. So plus friction into distance. Now friction is always mu r. Mu is 0.2 r into r. Now r is 2500. You can see that, and therefore I put it here, and I'll get my d as 27.96 meters, telling me that after distance of 27.96 meter, the body will stop. Body will stop because friction energy as eaten up is kinetic energy. That's what it means in simple terms. Okay, let's look at next problem. It says a body weighing 300 Newton is pushed up the plane by a 400 Newton force acting parallel to the plane. If the initial velocity of the body is 1.5 meter per second and coefficient of kinetic friction is 0.2, what velocity will the body have after moving 6 meters? So here's body's position 1, here is body's position 2 after 6 meters, and you are asked velocity in position 2. So we do exactly similar manner, write energy equation and see what is what. F into d this time is 400 into 6. 400 is along 6. mgh, see now I need reference. Now between these two I'll take the lower position as reference. So if this is my reference, mgh in position 1 is 0. Half mv square is half 300 by g into 1.5 square because see, body's initial velocity is 1.5 meter per second. And half kx square is 0 because there is no spring. Look at right hand side now. mgh for this will be mg, that is 300, into 3 because see, this is 6 angle given, it's not mentioned here, but in the data you take it as 30 degree. So if it is 30, this is 6 meter, so this height will be 3 meter, and therefore this mgh is 300 into 3. Half mv square I want to find, half kx square 0, and friction into distance. Now see, friction is always mu times the normal reaction, and d is 6. Now here if we write sigma fy equal to 0 in the direction perpendicular to the plane, this angle as I said is 30, so this is 30, and therefore r is equal to 300 cos 30, and therefore you can get r, which you can put here to get your v, which will be 8.942 meters per second. Okay, one more problem. A 30 kg crate slides down the path from A to B in the vertical plane as shown in figure. If the crate has initial velocity of 1.2 meter per second down the incline, we call it position 1, and it achieves velocity of 8 meter at its second position. See, this is second position, this is first position. Calculate the energy loss due to friction when particle moves from position 1 to position 2. Simple, we follow the same thing, and by the way, this data of 6 meter height is given. Alright, we write our equation. F into D 0, yes. mgh 30g into this height 6. I take this level as reference now. Half mv square, yes, v was given as 1.2. Half kx square is 0, is equal to mgh plus half 30 into 8 square. The velocity here is 8. Plus no spring, so half kx square is 0, plus friction into distance. Now this is sum total is asked. That's the energy, which comes to 825.6 joules, which is the energy eaten up by friction while going from here to here. Okay, thank you. There are more problems coming up in the next video.